Hi everybody, and welcome to our module on pulmonary function tests. Let's start by reviewing lung volumes. If we look at this graph on the right side of the screen, this is a classic pulmonary physiology graph that you can find in any pulmonary physiology textbook. And it shows the volume in the lungs over time as a patient is breathing. In the beginning of the graph here, the patient is quiet breathing. Quiet breathing is breathing without using any accessory muscles, using only the diaphragm to draw in air and then letting the air gently flow out. And when we are quiet breathing, there is a small volume of air that moves in and out with each breath, and that's called the tidal volume. And that volume is represented on the graph as the difference between these 2 points here, the volume moving in and out of the lungs with each quiet breath. If we were to forcefully push air out of our lungs at the end of a quiet breath and try to get the lung volume down as low as possible, we could push enough air so that the lung volume fell all the way down to this point here. That extra volume of air beyond the tidal volume that we push out is called the expiratory reserve volume. This is the extra air that can be pushed out with force beyond the tidal volume. Once we push all this air out of the lungs, what remains in the lungs, this small volume here, is called the residual volume. This is air in our lungs that can't be blown out no matter how hard we try. You cannot get your lungs down to a lung volume of 0. The smallest volume you can get inside your lungs is called the residual volume. Now consider if at the end of a quiet breath we were to draw air in and fill our lungs as much as possible. That extra volume of air that we could draw into the lungs is called the inspiratory reserve volume. This is extra air that can be drawn in with force beyond the tidal volume, and at this point the lungs are filled as much as they can be filled. We have a lung volume of just under 6 liters in a normal person. So a lung capacity is a sum of 2 or more lung volumes, and there are a couple of important capacities in the lungs, and we'll talk about those now. The first one is the total lung capacity. This is the sum of all the volumes in the lung, the residual volume, the tidal volume, the expiratory reserve, and the inspiratory reserve volume. If we go back to our chart on the screen, this is the total lung capacity here. It's the difference between the bottom all the way up to the top when the lungs are completely filled, and it contains all the 4 volumes we talked about in the last slide: the residual volume, expiratory reserve, tidal volume, and inspiratory reserve. The inspiratory capacity is the most air that you can inspire, therefore it's equal to the tidal volume, which is the amount you inspire with a quiet breath, and the inspiratory reserve volume, which is the extra volume you can inspire with force. If you look at this chart on the screen, this is the inspiratory capacity here. It's equal to the tidal volume plus the inspiratory reserve volume. Conversely, the forced vital capacity, or FVC, is the most air that you can exhale. It's equal to the tidal volume plus the inspiratory reserve volume plus the expiratory reserve volume. So if we look at this chart again here, this is the vital capacity right here, the VC. It's equal to our tidal volume plus our inspiratory reserve plus our expiratory reserve. So in order to blow out your forced vital capacity, you have to inhale to the maximum that you can, to this volume up here, and then you have to blow out all the air that you possibly can, which means you're going to blow your lungs all the way down to the residual volume, which is that volume of air that you can never get out of the lungs. And then finally, the functional residual capacity is the residual volume plus the expiratory reserve volume. And this is an important capacity because this is the volume that will be in the lungs at the end of a quiet breath, and that volume is modified in a number of pathologic states. So pulmonary function testing is the way that we clinically measure some of those volumes and capacities in order to assess patients who may have lung disease. The basic form of pulmonary function testing is called spirometry. In this test, the patient inhales until their lungs are filled to capacity and then exhales until they can no longer get any air out of their lungs. If you look at this graph on the right side of the screen, this is the typical type of data that you get from a spirometry test. So the patient begins exhaling at time 0 right here, and then as time goes on, a certain volume of air is leaving the lungs. Eventually this curve flattens out because the patient can no longer force any more air out of their lungs. So if you look at our graph on the left side of the screen here, what the patient is doing is the patient is drawing air in until their lungs are filled to capacity, and then they are blowing air out until the only air left in their lungs is the residual volume. So that volume of air that they blow out in going from filled to capacity to residual volume is going to be equal to the forced vital capacity, or FVC. And so that's one number you get from a spirometry test. This volume of air here, where the curve flattens out, is the forced vital capacity. You also get a second important number from a spirometer test, and that's called the FEV1, which is the forced expiratory volume in 1 second. That's how much volume of air goes out in the first second that the patient is doing a forced exhalation. And these two numbers, the FEV1 and the FVC, plus the shape of the spirometer curve, can tell us a lot about a patient's lungs and can help us diagnose various forms of lung disease. Now, before you can draw any conclusions about a patient's lungs, you need to make sure that their pulmonary function testing meets criteria for an adequate test. There are a number of criteria. You don't need to know all of these as a medical student, but some of the important ones are that there should be a sharp rise in the flow curve, like what's shown here, up to a peak value. And then the total expiratory duration should be greater than 6 seconds. So in some cases, patients have a weak effort and the result is a poor quality test. And when that happens, what you need to do is repeat the test until you get an appropriate effort and result from the patient. In obstructive lung diseases like asthma or COPD, the spirometry curve shifts from the red curve shown here for normal lungs to the blue curve shown for obstructive diseases. The problem in obstructive lung diseases is that air cannot get out and it gets trapped inside the lungs. This means that the forced expiratory volume in 1 second is going to be reduced because it's difficult to get air out. There's slow flow of air out of the lungs. There's also going to be a reduced forced vital capacity because air is trapped and less air gets out. And you can see both of these things on this curve here. The FEV1 has fallen like so, and the FVC, which is up here, has now fallen down to this level here. Also notice that the FEV1 falls a lot more than the FVC. This means that the ratio of FEV1 to FVC is going to fall, and that's the hallmark of obstructive lung disease. Later we'll talk about restrictive lung diseases. In restrictive lung diseases, the FEV1 to FVC ratio does not fall. So this pattern is what you get with obstructive lung diseases. If the patient has asthma, the pattern is reversible. You can give the patient bronchodilators and their lungs will look more like a normal lung curve. In patients with COPD, it's a chronic disorder. That's what the C is for, chronic. And so in these patients, there's a very small or no change with bronchodilators. But in both cases, you will get an obstructive pattern, meaning a reduced FEV1, a reduced FVC, and a reduced FEV1 to FVC ratio. So I just told you that the forced vital capacity falls in patients with obstructive lung disease, but you should know that this is the only important volume or capacity that falls in obstructive lung disease. Most of the other volumes and capacities go up, and that's because there's air trapping in obstructive lung diseases. So for example, the total lung capacity, the functional residual capacity, and the residual volume, all of these things go up in obstructive lung diseases. The FVC is the only important capacity that falls. Now let's talk about flow volume loops, which is an alternative way to represent the data from a spirometry test. So on the last slide, we showed spirometry data with time along the x-axis and volume of air exhaled along the y-axis. Another way to represent the data from a spirometry test would be to put volume along the x-axis here and put volume per second, which is flow rate, on the y-axis here. And we could make zero flow rate be this point right here. At the bottom, we've got air coming into the lungs, so this is inspiration. And at the top, we've got air going out of the lungs, so this is expiration. And so when we plot the data from a spirometry test this way, we get a loop that looks like this example on the screen. This is a typical pulmonary flow volume loop. So to understand these loops, the first thing you have to recognize is that high lung volumes are shown on the left of the x-axis and low on the right. This is just a convention in the way it's always done. Also, this point in the middle is zero, meaning no flow. And as I said before, up here is when air is being exhaled or going out of the lungs, and down here is when air is being inhaled. So let's start at this point right here where we have this volume of air in the lungs and no flow. At this point, we've asked the patient to inspire and fill their lungs to capacity, and therefore they fill them to this volume right here, but there is no airflow. We now ask the patient to begin forcefully exhaling air from their lungs. As a result, we begin moving this way towards lower lung volumes, and the flow of air begins to go up towards the top where we have expiratory flow. Initially, the flow rate goes up very fast, but then the flow rate begins to taper and we get back down to a zero flow rate. And at this point, we are down to our residual volume. The patient has blown all the air out of their lungs that they can get out. We now ask the patient to begin inspiring, and the volume starts to go this way towards higher lung volumes. Initially, there's a high rate of air coming into the lungs, but then it tapers off and goes back down to this point here, where once again the lungs are filled to capacity. So this is the way to understand these flow volume loops. You've got expiration going up this way and inhalation going up this way. You start at this point with no flow and you end at this point with no flow. At this point, you're at maximum lung capacity. Over here, you're at the residual volume. So now let's take a look at what happens to flow volume loops in disease. And first, we'll talk about obstructive disease. So when patients exhale, initially there's a very fast flow rate as patients blow out, but then the flow rate starts to taper off. And this portion here where it's tapering off is highly dependent on flow of air through the bronchioles and bronchi. And if there is obstruction, that portion will become abnormal. So this portion begins to have an indentation in patients with obstructive disease, and the indentation gets more severe depending on the obstruction. And this shape is the shape that you need to know to understand obstructive lung diseases and flow volume loops. Now let's talk about restrictive lung diseases. These are disorders where air cannot get into the lungs, and because the lungs can't fill, because they're restricted from filling for some reason, less air gets in and therefore less air is necessarily going to get out. If you look at our graph again from spirometry on the right side of the screen, patients with restrictive diseases are shown on the yellow curve. Notice that the FEV1 falls just like it does in obstructive disease. The FVC also falls just like in obstructive disease. The big difference, however, is that the FEV1 does not fall as much in restrictive disease as it does in obstruction. Therefore, even though you will have a reduced FEV1 and reduced FVC from less air coming in and less air going out, in restrictive lung diseases you have a normal ratio of FEV1 to FVC. This is the hallmark of restrictive lung disease, a normal FEV1 to FVC ratio, and normal is about 80% of predicted or higher. Also, in contrast to obstruction, patients with restrictive lung diseases do not have increased volumes, they have reduced volumes. So the total lung capacity, the functional residual capacity, and the residual volume, all of these were increased in obstructive lung disease. All of these are decreased in restrictive lung disease. So you can just remember restriction means reduced volumes. So let's go back to this slide showing our flow volume loops. We've got a normal flow volume loop here. We have mild and severe obstruction. In both of those situations, you get an indentation to this portion of the exhalation curve. And then this is what restrictive lung disease looks like. Basically, it's a much narrower flow volume loop, and that's because there's less air coming in and less air going out. For completeness sake, I'll show you a final important flow volume loop that's high yield for your boards. This is what a fixed airway obstruction looks like. Basically, it's just almost like a square here, and that's because there's some obstruction not allowing the airflow to get up into this portion here. This is what you can get when you have a mass obstructing the bronchi or the trachea. And then one other thing I want to point out here is that notice where the normal curve here is. In obstructive lung disease, the curve shifts this way. That's because, remember, we've got higher volumes down here at this portion of the x-axis. And in obstructive lung disease, air is being trapped and the volumes are increasing. In restrictive lung disease, the curve is shifting this way. This is because this is the lower end of the x-axis in terms of volume, and you have lower volumes in patients with restriction. And here I've just shown this in greater detail. The blue is a normal curve, the green is how the curve would shift in someone with obstruction, and the red is how a curve would shift in someone with restriction. In another video, I talk in detail about the causes of restrictive lung disease, but just briefly here I'll mention that there are two reasons you can have a restriction of air filling the lungs. The first reason is if your lungs are healthy but you have poor breathing mechanics, meaning there's something wrong with the chest wall or the respiratory muscles. The second reason you can have restriction is because you have interstitial lung disease. This means there's a disease process of the lungs that is restricting them and keeping them from filling normally. So if someone has a restrictive pattern on their pulmonary function testing and you want to know whether the problem is interstitial lung disease or poor breathing mechanics, there is another measurement you can make to help differentiate those two, and it's called the DLCO, or the diffusing capacity of carbon monoxide. This is a test that measures the ability of the lungs to transfer gas. The way it works is the patient inhales a small amount of carbon monoxide. This amount is not dangerous. The machine measures the carbon monoxide that is exhaled, and from that it determines how much capacity the lungs have to take up gas. A normal result is 75 to 140% of predicted. In patients with severe forms of lung disease, it can be less than 40% predicted. So in a patient who has poor breathing mechanics, for example, problems with their respiratory muscles, the DLCO will be normal because the lungs are healthy and gas exchange is normal. In contrast, in a patient who has interstitial lung disease, the lungs are not normal. That patient will have restriction on their pulmonary function testing, but will also have a low DLCO. And this is a list of some of the conditions that can cause a low DLCO. The classic one is interstitial lung disease. This is a form of restrictive lung disease. Patients with emphysema can also get low DLCO. And then the other group are patients who have problems with blood flow through the lungs. These are patients with pulmonary hypertension or pulmonary embolism. These three at the top are the main ones you see clinically. Some other rare causes of a low DLCO are if parts of the lung have been resected, or patients who are severely anemic. They will have a low DLCO, but it'll correct when you adjust it for the hemoglobin level. And I talk more about the DLCO and how to use it to diagnose lung conditions in the video on restrictive lung disease. And that concludes our module on pulmonary function testing.